All right, so let's talk about Pascal's principle. And the best way to talk about Pascal's principle is just to dive into a practice problem. Now, what is Pascal's principle? Well, Pascal's principle, it mostly applies to incompressible fluids. So this is going to be mostly liquids. So incompressible fluids, the reason why we need these is because when we change the amount of pressure, the volume doesn't change significantly. So when we're talking about Pascal's principle, this basically states that pressure will be transmitted equally and undiminished throughout the entire liquid. So if we're talking about these pistons over here where we have a hydraulic system, we're basically saying that the pressure applied to this small piston over here is going to be the same exact pressure applied to this large piston over here. So we can model this as P1 equals P2. This is just going to be small piston, large piston. And since we also know that in general pressure equals force over area, we can devise the equation that force of this small piston over here over the area is going to equal the force of this large piston over the area of that large piston. So this is actually going to be a very important equation that we need in order to find the force that is exerted from that large piston, since we're talking about small piston that is pushing down, and vice versa. So let's actually start with our first part of this question. So we know that our small piston has a radius of 5 centimeters. That's going to be important for trying to find our area. Large piston has a radius of 20 centimeters. Remember, we have radius, not diameter. And just as a refresher, radius is half of the diameter. Now, you apply a force of 500 newtons to the small piston. So now the first part of the question is, what is the pressure exerted on the fluid by the small piston? Well, we need to first find our area. So we're just trying to find the pressure that is exerted by this small piston. So we know that area is going to be pi r squared. So that is just going to be pi times, we need to convert this to meters, so this is going to be 0.05 meters, and this is squared. And when we do the math for that, we are going to get 7.854 times 10 to the negative 3 for our area. And that's just going to be for our area. So all we have to do, we're given the pressure, or we're given our force. So our pressure is just going to equal 500 newtons over, and I'm just going to copy paste this guy over here. This is going to be in meters squared. But just to make it simple, I won't be writing those units. I'll just write it over here, meters squared. So 500 newtons over 7.854 times 10 to the negative 3 meters squared. And that is going to get us, let's see what that gets us. We're going to get 63,662 pascals, or if you wanted to, it would be 63.7 when you round up kilopascals, but we're just going to go with pascals. So our pressure that is exerted from this small piston is 63,662 pascals. All right, so what is part 2? It asks us, what is the upward force on the large piston? So to find this, I'm just going to be erasing some of this stuff over here. Let's take that out and this guy over here. Okay, so, and I'll just move these over here just to have our equation. This is our important equation over here that we need for Pascal's principle. So we know that our pressure P1 equaled 63,662 pascals. So we know the pressure from that small piston. Now we need to find the force that is created from this large piston, that is exerted by this large piston, that upward force. So what is that force? Well, we know the pressure. So this is 63,662 pascals, and this is going to, let me actually just delete this portion over here, because this is going to be representing our P1, our pressure. That is going to equal the force of our large piston. We'll do F2, and then we need to find the area. So area for this guy is just going to be pi r squared, which is going to be pi times 0.2 meters squared, and finding that area, we are going to get 0.126 meters squared. So this is 0.126 meters squared. So all we have to do is just multiply 63,662 pascals times 0.126 meters squared, and our force for this large piston, that upward force, is going to end up being 8,021.4 newtons. So this is our force over here. So now let's move to question 3. Now, if the small piston moves down by 20 centimeters, how high does the large piston rise? So for this question, we're going to be using a different equation. So let me just remove this stuff over here, and we're going to need our area. So our area over here for our large pistons is 0.126, and our area for our small piston, we'll just do A1 equals 7.854 times 10 to the negative 3 meters squared. All right, so we're talking about height. We want to know how high does the large piston rise, assuming that the small piston moves down by 20 centimeters. So when we describe Pascal's principle, it was pressure that will be transmitted equally through the fluid, which also means volume is conserved. Now, in our hydraulic system, volume will be conserved, and volume equals area times our depth. So this is going to end up being, since our volume is going to be the same, we're going to derive the equation V1 equals V2. So the volume that is compressed over here will be the same over here. So, well, what does that look like? How can we derive an equation with area and density, or not density, depth? So we just have to do the same thing that we did with our pressure, where it's just going to be A1 D1 equals A2 D2, because we know our volume is going to be conserved. So area times depth over here is going to be area is going to equal the area times depth over here. So we're already given our variables for our small piston over here. We know this moves down by 20 centimeters. So I'm going to be doing this over here. So we know that our area is 7.854 times 10 to the negative 3, and I won't put it in units just to make it a little bit more simple, and this is going to be times 0.2 meters, and this is going to end up equaling, we need to find our how high does a large piston rise, that sort of depth or distance, and this is, we know our area, which is 0.126, and then we'll put D2. So all we have to do is, and I'll move this guy over here, we just have to divide our 7.854 times 10 to the negative 3, our area and depth for the small piston divided by the area from our large piston. This is where we find how high that large piston rises. So if we do that math real quick, we have that. How high the large piston rises is going to be 0.0125 meters. Now for our final question, we're asked, what is the mechanical advantage of this system? Well, we need to know the fact that mechanical advantage is going to be force output divided by force input. So how much force are we putting out and how much force are we putting in? Well, if we remember, we are, for our answer for, what was it, number 2, our upward force was 8,021.4 newtons, and our pressure, or the force that we applied, was 500 newtons. So this is going to be 8,021.4 newtons over 500 newtons, and we're going to get about 16. So our mechanical advantage is 16, which is actually really great. So when we're looking at these hydraulic systems, we're applying Pascal's principle to get a great mechanical advantage. So the beauty about hydraulic systems and Pascal's pressure or Pascal's principle is that over here with this small piston, we only have to apply a little bit amount of force to get even more force from this large piston. So all we have to do is just, apply 500 newtons of force, and we get 8,021.4 newtons of force from that, John. Now, what you'll also notice is that we have a smaller area over here. So when we have a smaller area, we need to compensate by pushing this smaller piston farther, because over here the amount of meters that this large piston pushed up was 0.0125 meters. That's literally nothing. And over here we pushed it by 0.2 meters, which is a little bit longer. So with our mechanical advantage with our hydraulic systems, although we apply less force, we need to apply more of that depth in order to produce this amount of force. So hopefully that made sense to you guys. Pascal's principle is one of the most fascinating things, and that's pretty much it.